Welcome to Datadog Illuminated. Let's talk about security scanners, specifically ones that scan static code. These scanners run deterministically, and they rely on a fixed set of rules to catch vulnerabilities in your code. They're widely used, therefore, it stands to reason that using them has a net positive effect. But there are some shortcomings to using this approach to finding security flaws. First, these scanners can flood engineers with false positives, so developers naturally learn to tune out the findings. Then, when the scanner catches a real vulnerability, it can slip past engineers who are too fatigued to notice. And another shortcoming: these static code security scanners can't understand context. They look at only one file at a time, and they can't trace whether input from outside the system, something an attacker could actually control, flows downstream into the found vulnerability. Without tracing that path, there's no way to know if a flaw is truly exploitable and deserving of an urgent fix. Bahar Shah is a staff engineer on Datadog's code security team, and she and her team built an open source tool that fixes both problems. Instead of relying on deterministic rules, it uses LLMs to actually reason about whether a flaw is exploitable. But I have questions. How does the AI-powered security scanning software give the LLM the context it needs without bloat? Is it expensive to use AI to reason about all of the code in the entire system? And does this AI native security scanner truly produce results? How are those supposed gains defined and measured? Thank goodness Bahar is here. Let's do this. All right, I'm here with Bahar. Bahar, will you introduce yourself, please?
Of course. Hi, everyone. I'm Bahar Shah. I'm a staff engineer on our code security product. So working on a variety of different product areas, but everything code security.
Everything code security. And right now we're going to talk about how Datadog finds security flaws in code using AI. I think to give us context, let's start with how did Datadog find security flaws in code before AI?
So to do it, I'm going to throw out some acronyms. I will also explain those acronyms as we go, though. There is a concept called static application security testing, SAST, S-A-S-T for short. All this means is it basically analyzing source code vulnerabilities to find issues or potential security concerns in your code.
Static application security testing, SAST. And you said that scans source code to find security vulnerabilities. Can you speak to the static part of it?
Yeah, so the idea is that these are the files themselves, right? So there's no concept of what is actually running. There's no concept of the active, executing code. It's purely at the raw file level. And that's kind of why it's called static testing.
So it does the scan, it scans the source code, it's not running it. And then it's looking, what's it doing? Regex?
Traditionally, and not all SAST scanners, but the majority of SAST scanners are generally using some sort of pattern matching, whether that's regex, whether it's syntax matching, things like that. So it's generally very deterministic, but also relatively limited in how it's constructed.
So this sounds cool, but I guess it must be some issues with it if we needed to bring AI in. So what are the problems with SAST?
Probably the biggest one, and it's well documented, Google even did a study back in 2018 around this piece specifically, is false positives. Because if you're doing kind of a pattern-based or a regex-based approach, you don't really have context, right? So you can't really answer the question of, is this actually real, or is this trusted, or any of those types of questions. And so false positives is the biggest reason that people don't actually adopt SAST tools. And so that's kind of the first thing that we are trying to fix.
I'm imagining the fatigue I get when Code Cloud asks me yes or no over and over and over again. At first I pay attention and read it and understand, and then by the 10th one, I'm like, yeah, sure, just fine. Go, whatever it takes to make that go away.
That's exactly it, right? And when you're talking about kind of security vulnerabilities, that's the worst case, right? If you get to the point where developers are like, it's probably false, so I can just ignore it. But yeah, all it takes is, a few times where what you're ignoring is actually real before it's a big problem. So because, right, a lot of these are kind of regex based, so writing rules and adding new rules and kind of updating can be very expensive and brittle. It requires a lot of manual effort, and it requires a lot of intricacies and understanding kind of the details nuance of those languages and the rules themselves.
And then when things change, they're hard to change. Yeah,
exactly.
I feel
Exactly.
you. Uh-huh.
The biggest one, and it kind of relates to the false positives as well, right, is just, once again, generally most SAST tools, you're kind of only analyzing a single file at any given moment. So you don't really have any multi-file, multi-step analysis happening. So, right, if your functions are defined in outside of the file that you're looking at, if your variables are being defined or passed through from other places, you don't really have that context at all. You're really just kind of stuck with a very, very narrow view of what you're actually trying to determine if a vulnerability is present in.
So it doesn't have the context of the surrounding file. So it doesn't understand what's coming in necessarily, where it's going afterward. I can guess because of LLMs are coming in later, that a problem might be that it has no semantic understanding of what's going on. Yeah, I can infer that one. Are there any others?
Those are probably the biggest ones. I think generally then, right, like traditionally SAST tools also, they're a little older, they're a little more legacy. And so a lot of them haven't caught up yet with kind of the new class of AI specific vulnerabilities that have started popping up. And so, eventually some of these tools will catch up and will add support for those. But there is a very real gap happening right now where there are new types of potential attacks being introduced, but the scanners haven't necessarily been updated to detect them.
Are there like industry-wide scanners, or just like did Datadog maintain their own scanner?
So Datadog, we do have our own industry standard scanner. It's called the Datadog Static Analyzer. It is exactly what we're kind of describing, right? It uses regex. It's a little bit more deterministic and all of that. And so we package it as a binary used by hundreds of customers.
Sounds like we've improved upon our methods. Will you tell me about that?
Yes. So, right, some of the stuff that we just talked about, right, with some of the issues that are present in kind of traditional SAST, started us thinking, okay, well, how can we make some of this better? And that's kind of brings us to what we're calling AI native SAST. At a high level, right, the idea behind AI native SAST is, can you use LLMs to basically reason about your code and identify potential issues instead of relying on some of these predefined kind of legacy mechanisms or legacy rules?
Instead of relying on patterns.
And then specifically, right, can you do it in a way that reduces the false positives, kind of, fixes that alert fatigue that we were talking about?
So it has the same goal of finding vulnerabilities without so many false positives.
Yeah, so it understands like code semantics. It understands the data flow, the execution flow. It understands kind of, the actual usage of the code, as well as the context. So where are files defined, where are variables passed through, things like that.
So we got the problem, we got the solution. What I want to know next is, how does it work?
The first step starts with kind of identifying relevant files. But before we even get to that, right, what's the action? Well, there needs to be sort of trigger, right? And so in our case, any code change that happens in Git, as long as our product is enabled, is basically sending us a event. And so we're taking that event, and then from there is kind of where we're starting our entire analysis process.
So a scan is triggered. And then what happens next?
Think of it as anytime someone pushes a commit to a branch, that basically will trigger a scan on our end. So the first step is all about identifying relevant files. And the reason we need this, right, is we don't want to analyze the entire repo every single time. So the idea is, once we've kind of created a baseline of these are all of the vulnerabilities present in your code base when you first onboard a code base onto our product. After that, it's all about, okay, how do we make sure we're only analyzing the files that we need to? And the reason we kind of do this, right, is one, like I said, we don't want to scan the entire world, but we also want to make our analysis and kind of the information we're passing to LLMs eventually like very targeted, right? Because what we found is if you give too much context, that is an issue with LLMs.
So it's triggered by Git operations. So there's some sort of diff, and then just the code changes are passed in. So it only needs to understand the code.
Yeah, not quite. So in our case, we actually will treat the push to Git as a chance to say, let us look at everything that's present in your code base. But obviously very expensive if we're literally scanning files that haven't changed each and every time as well. Using, caching and kind of previous results and all of that, we basically will still take in the idea of these are things that are already present in your code base, but then we're also kind of looking at, okay, what is actually changing? So we do end up having a diff. It's just not necessarily a straightforward diff of saying like these are the only files. We're actually doing a little bit of a hybrid approach.
So it understands the whole repo, but it knows like what's previously cached versus what's not, and then it's looking out what's not cached? And then what's it doing with that information that's not cached?
Yeah. And so the first step we do is, so as part of this trimming down or trying to identify like what is actually relevant, right? So we know kind of different types of vulnerabilities that we specifically are looking for. And so we want to basically see, do we think certain files or the contents of certain files are applicable for scanning? So we use a combination of different things, heuristics, keywords, et cetera. We're trying to kind of identify potential areas where a vulnerability might be occurring, and then basically decide, okay, we think something might be happening here, and then now maybe we need to go to the next step in the whole process. So, here's an example. We had developers that were in the process of making a service that basically was taking application logs and just more or less feeding them directly to an LLM for sentiment analysis and categorization. Mm-hmm. And so it's a potential prompt injection, right? In this case, because you're taking, basically unverified user input and then ending up directly passing it into an LLM prompt. And so you could do things, right? Like ignore the previous system prompt, like go do whatever you want now. And so that is a new class of vulnerability that's being introduced, obviously, with so much AI usage. But in this case, this was a very real example that we caught as part of our static analysis process.
This makes so much sense to me as a developer, why you would want to do this. That's why I love this example. Like, yeah, I want to categorize all my logs and understand larger behavioral issues that I might not catch by looking at them. All right, so here's our use case. What happened with our example use case here?
In this case, for a prompt injection, right, we basically want to identify places where prompt calls or LLM calls might be happening, right, where agents might be being invoked, straight prompting is happening, things like that. And so this first step of identifying relevant files, it's a combination of us literally looking for, literally like patterns in the code, like, prompts, certain types of function calls, things like that. And so in this example case, right, we basically flag that, hey, there's a file here where there's a input that is being passed in directly into this function, and it's going straight into an LLM prompt. It doesn't look like there is anything else happening, right? We're literally taking raw text and just putting it directly into a prompt.
It's triggered by a get change. This step is looking for relevant files. It's not looking at the whole repo as we discussed. It's looking at cache results, and what's not cached is the new stuff. It's using heuristic and keywords, and then it's able to say like, hey, this has an input into this LLM, and we don't know where this input came from.
And in this case, it might be a prompt injection, right? So we're basically saying this is something that passes our first check or our first filter gate to say, hey, we think this needs further analysis. So right now, this is actually purely deterministic. There are no LLMs involved in the initial filtering down process.
No LLM.
So at this point, right, we know enough to say in our example, okay, here is a file, it's making a prompt call. It looks like it's taking some input directly in and just jamming it into the prompt, right? So we've found a file that we think is relevant.
Okay, cool. And so now that we have that relevant file, what are we going to do next?
So the next piece is all about getting context. So we talked about, right, like a little bit earlier, we kind of mentioned one of the pitfalls or kind of weaknesses of traditional SAST tools are that you don't necessarily have the multi-file context. You don't necessarily have the deeper complexity analysis. And so in this case, our context retrieval is all about, okay, so we know in our example of the logs and the prompting, we know that there's some sort of text that's being passed in directly to the LLM prompt. For us now, the context retrieval is asking, okay, where is this input coming from, right? What is it? And so what we do is we actually trace through and detect where is this variable coming in, like what are the functions it's passing through, where is it being modified, where was it either initialized or where was it first seen, all of that type of things. And generally, there's actually a term for all of this. It's called data flow analysis. And so data flow analysis, right, it's all about tracking how values are moving through a program or through your code. So from creation all the way through to actual ultimate usage and where they're used. And so our context retrieval is all about this idea of, can we actually determine where and how the information, the variables themselves are actually being used and being referenced.
So it's building context for data flow analysis. So like the cross-file thing that we talked about that it can't do is exactly what exactly what we're doing here.
Not yet. You can do this with an LLM, and this is something that we're currently kind of experimenting with to see if we want to replace with an LLM approach. But right now, we're actually building this context manually, right? So we're actually creating syntax trees of what the code looks like. We're actually identifying where the functions are defined, where they're actually being passed through, and then that's kind of where we're constructing this context object from.
We have the dev speak as service that feed app logs to an LLM. When AI native SAST hears about it, it's like, oh, hey, the LLM has an input that we don't know where it came from.
So step 2 is basically all about saying, okay, where is that data coming from, right? And so what we do is we basically identify all of the places where that variable is actually passing through. So, and we're gathering kind of, right, like the files themselves. So like if it's being modified in a function, we're taking, kind of collecting that function as part of our context. And then we're basically tracing it all the way back through to where it eventually came in. So in this case, it was coming in from logs, right? And so we were able to basically trace it all the way back to, okay, this is the first place that we see it, where it's actually inputting into the system. And then from there, right, we've kind of built backwards this entire context tree of where and how it's actually being either modified or used.
So it sees that the user logs are making it directly into an LLM prompt. Understand it, but I'm tickled by the security mindset in general, where it's just like any chance for a user to have any input into the system is a potential for attack. It's like a pessimistic view of humanity.
But yeah, and it has a term, right? So for the security side, it's called taint tracking. It's a type of data flow analysis, but yeah, in this case, you're basically tracking any untrusted input. So right, think like user input, HTTP request, logs in this case, basically anything that we don't have direct control over, or like your code doesn't have direct control over. You basically just say, hey, this is tainted. So you assume the worst, and then you basically track down where and how it's used, and like whether it's actually reaching like a sensitive operation or being used in a sensitive operation all the way to the end.
I don't think everyone's bad. I don't think most people are bad, but I think at least one person is bad.
Yeah. And all it takes is one malicious actor, right?
Does that bring us to step 3?
So step 3 is, okay, so we've identified all the files, we've kind of gotten all the context. Now we're finally getting to the AI part of the AI native SAST. So this is our AI analysis step. So the input to this step is, in this case, it's basically everything we've gathered, right? So it's the actual file that we've identified as, hey, we think there's a vulnerability present in here. It's the context we've built around, look, these are all of the inputs or like the variables that are being referenced in that function or in the location that we think is vulnerable. This is all of the relevant context or relevant file information. And then now it's also, hey, these are specifics around the type of vulnerability that we think is present. So in our case, like, right, we kind of want to say, hey, we think there is a prompt injection happening. So it's a little bit of, guiding the LLM, say, really focus on this use case and tell us if this is actually happening.
And so much with working with LLMs too is like, how to give them just the right amount of information.
Exactly.
So how does it work?
So we do a 2-shot model. So we actually make 2 separate calls as part of our AI analysis. So the first one is a kind of faster and cheaper LLM pass, right? We're using a smaller LLM. The whole point is to basically do kind of a quick sanity check, yes or no, is there a vulnerability present? So it's all about kind of a very fast, cheaper detection of we think something is present. Don't necessarily go into too many details just yet, though. With a smaller model, more yes or no, not necessarily kind of deeper reasoning, you will see more false positives potentially, which is why we do a 2-step process here. But the idea is kind of do a quick pass first, and then we'll do a follow-up deeper dive if we need to.
That makes sense to me. Like you would want too many false positives, not 2 false positives. That's one thing gets through is really, really bad. If some extra false positives get through, especially now because there's no human involved yet.
Yep. And so going back to our example, right, in this case, that first step detection, what it's going to identify or kind of look for in this case is it's going to see, of all of the information you've passed to me, there is no sanitization happening of this user input, the logs in this case, right? There's no validation, there's no parsing of it. It's just straight being passed in. And so it's going to flag it as, hey, like this is actually a vulnerability present.
I'm just going to write flag.
Yep. So the first step, right, says, hey, fast detection, we think something is present. The second one is a more thorough LLM pass. So in this case, we're using a larger model, a more expensive model with higher reasoning or better reasoning and deeper analysis. And so This one specifically is looking at the data flow. It's looking at the exploitability options. It's really kind of looking for the sources and the sinks, all right? Like where is the potential malicious input coming from, and then where is it actually being executed or run? And so that deeper pass is all about really making sure that we are confident in that result. So we actually ask the LLM in the second pass to also, basically rate itself, assign a confidence score of low or high, depending on how real it thinks the finding is and its own reasoning. And we actually kind of are a little antagonistic with it as well, right? We basically are saying, hey, as part of our prompt, we're like, look, a security tool found this thing, thinks it's a vulnerability. We're not sure, like you need to convince us, right? And so we're kind of very much focused on the prove it to us, not just a, hey, validate that this is actually a thing.
So it is outputting yes or no, but it's also giving a lot of reasoning. It's not just simply a yes or no.
It's giving
what I'm hearing.
Yep, exactly. And in our case, we very much focus on the data flow piece. So we actually say, give us specifics about the sink, the source, the actual data flow.
What, where, why, when.
Exactly.
Like all the things we had to know, and confidence level. So right now, for example, the fast and cheap LLM has flagged it as suspicious. And so the thorough LLM pass, it's saying is it truly a problem? Like this one looks suspicious. So there's a yes or no. And then it's also going to output, in our case, yes. And here's exactly why.
Exactly.
Okay.
Yep. So in our case, it actually, right, it ended up telling the developer in this case, your input that is being read from here in this file over here is being directly passed into this LLM call that's happening in these files, 4 or 5 files down in. This is an issue, and this is why it's an issue.
Confirms issue with reasoning and says why.
There is kind of a step 4 here, our final catch-all, post-processing stage. At this point, right, we've at least said, okay, these are all of the potential vulnerabilities, or these are the vulnerabilities straight out that we think are present in your code. But we want to do a few more things. So we want it to be actionable. So we basically, if we didn't find anything, or if we think that there is not a result found, or we found something that we think is low confidence, we actually drop it. So we only will show to the user something that we think is either actively malicious or actively a confirmed vulnerability. So anything that's benign, anything that's not confirmed, we drop straight out.
No human involved. Let's not waste anybody's time with this.
Yep, exactly. But the biggest piece that we do as part of our post-processing is actually the caching. So if you remember when we talked about kind of the very beginning with the identifying files and kind of the deterministic diff that we try to do, this is all right based off of the results of previous scans and kind of things that we've already identified. So as part of our post-processing, we update our cache with new findings, with relevant information that might have changed, all of that. And the output of the kind of this post-processing stage is a Serif file, SARIF. And so that Serif file, so that's where our tool actually updates it. And Serif it's a standard in the industry. So all static application tools basically output this type of file. We will output a Serif file, and then we basically will process it as part of the Datadog processing pipelines. And we do kind of various things with that, right? Nope.
I'm hung up on something you just said, so I'm going to take you back to the results being cached. The results are cached regardless of whether it's vulnerable. Yes. I imagine, right? So you don't read. Okay.
If we found something, if we didn't find something, we basically say this is what we know for this file, and the details that we're tracking. This is everything we know. But then what we actually will put into a Serif file and populate into that file to actually surface to users is only the things that we've said these are confirmed vulnerable with high confidence.
So the first thing you do is cache results. Then if benign, drop it from there.
Yep. If benign, drop it. If confirmed vulnerable, keep.
Okay, so we output this Serif file.
Yep.
And then I believe you were telling me what the Serif file does.
So the Serif file, it's a file. It's like a JSON format, right? The more interesting thing is, what do we do with it once we've kind of outputted it and we've kind of, we've started processing it. So this is where kind of other pieces of Datadog or other parts of our product come in. If you remember, I kind of mentioned in this logs example, right, that the developer was basically notified, hey, your code is potentially introducing a prompt injection, right? So the way we do that is actually using like pull request comments, notifications directly on the pull request. So in this case, and this is an integration that we have as part of our code security product, once we identify like net new vulnerabilities, wherever they're being introduced, we'll actually kind of try to surface that. So for developers, in this case, we're showing them on pull requests with like via an IDE extension as well. Kind of there's various places and pieces where we'll try to hook in and like show where vulnerabilities are being introduced. But in this case, we left a PR comment notifying the developer that, hey, there is a potential prompt injection being introduced. And then all of this information that we talked about, you know, the data flow, the sources, the sinks, kind of some of the context on the actual type of vulnerability and what a prompt injection is, all of that gets like packaged together and we leave it as a comment on the pull request. So the developer can actually see in real time as they're making their changes what the security issues that they might be introducing are.
So that Serif file, that format allows you to customize the way you surface the findings to the team.
It's exactly that. So we upload those Serif files from our tool like into the Datadog processing pipelines. And then as part of that processing downstream, we do various things with the results that are within the Serif. So some of it is what I just talked about, kind of the PR commenting. Some of it is, right, we actually like show it in our own internal UIs. We write it out and like you'll see it shown up on different dashboards. There's kind of different places and different ways that information gets shown and surfaced, but it all is coming and being powered from that Serif format.
Can you integrate with other like Datadog products? I'm thinking like, can this be automatically remediated with?
That is exactly one of the things we do. So, you know, as we leave a comment on the pull request, you can actually like tag like at Datadog bits to actually fix it. You can also fix it via our UI where we show the details of the vulnerability. There's actually also a big button that says, you know, remediate this, and we can kind of kick off whether it's an AI assisted remediation session or, you know, you can kind of chat back and forth with an agent and go back and forth on the fix. Because at the end of the day, it's not enough to just detect, right? You want to also prioritize. You also want to be able to actually remediate. This AI native SAST process that we've talked about is kind of all of the detection, but then the real kind of, you know, usage and functionality comes from, okay, the prioritization pieces, which we help power with some of the context that we can do as part of our analysis. And then the remediation is really kind of that last step in closing the loop.
So the remediation is like something you could do yourself. It's not part of the AI native SAST itself. Yes, exactly. It's just
think of it
setting up for...
Exactly. Think of it as like another output of what we are helping to power.
Yeah, and you're setting up the user to remediate in whatever way works with their particular teams and their particular workflow.
Exactly.
And maybe that's also auto-remediate with Datadog, but also maybe it's not, depending on whatever the customer wants. I happen to know that this is actually an open source project, right?
Yes, our Datadog's AI native SAST tool is open sourced. It is available on GitHub in the Datadog SAST repo as part of the Datadog organization. Basically, as long as you bring your own LLM API key and a Datadog API key, you can run it yourself and you can actually find vulnerabilities in your own source code without having to go through the full integration process.
Just to bring it home, we need to take our example through to the post-processing step.
Yeah, so at this point, from the post-processing angle, right, what it looks like is the results kind of are surfaced to the devs in a variety of ways, like we talked about, right? So some of it is PR commenting, some of it is within the UI, but it's surfaced to the developers, and then it's also providing them with that context. So making sure they understand the actual issue. How do we make sure that they have enough information then to go take that action, whether it's auto-remediating, whether it's going and looking at the code, whether it's talking to someone.
So it's just like, here's the problem and why, or does it recommend steps?
Some of it will recommend. For prompt injections, for instance, we will actually recommend some changes. For other types of vulnerabilities, it might just be as straightforward as saying, here is the vulnerability, here is the information and how it's kind of being used and passed through. And then it's up to the developer to kind of figure out maybe for themselves or do a follow-up using one of our auto remediation or like AI assisted remediation mechanisms. But in this case, you know, they will get information or context around prompt injections that tell them you should be sanitizing your input. Here are some examples of what you could do, things like that.
I included actionable steps in this one, even though it's not always there, because in our example, prompt injection, it is there.
At the end of the day, like a developer should actually have everything they need and ideally actually just be able to do it as simple as like, you know, clicking a button or kicking off a session, and everything will kind of be fixed with the suggestions that ideally we're populating. That's kind of the vision of what we want to get to.
So I want to talk briefly what I think I see in the story are some steps like these first two that don't use the LLM or this fast, cheap scan. I think I see some steps where we're being mindful of cost. Is that true?
Yes, 100%, right? Like as we said earlier, you can't scan every single file for every single vulnerability for every single time a code is being pushed. It'll go bankrupt before you can even do anything, right? And so the idea is, yeah, we want to only ever actually do a full repository scan when a repository is first onboarded into the product. And then after that, we want to kind of try to limit and really use AI in a way that is really kind of what can't be done in a like more legacy or traditional way, right? So in our case, with some of the file matching, with some of the context retrieval, these are things that, as I said earlier, we are exploring potentially moving bits and pieces of it to a more like agentic approach. But at the base of it, there's still fundamentally, there's still a core of this, which we probably won't ever actually replace fully with an LLM, partly because, yeah, it doesn't make sense from a cost perspective, but also if what you need are deterministic results for certain steps, then you're actually better off doing it in a non-LLM use case sometimes.
Let's do a quick exercise. So what I want is for a pink star to represent that something can be cost optimized. So one thing you said, full repo scanned only at onboarding. That's a cost optimization step, as is the diff, triggering on just the diff, right?
Don't analyze the whole repo. And really kind of that whole step one is more or less cost optimization.
Using the cache results. Cool. For these two, they get stars?
Yep, yeah, exactly. Yep. Yeah, because the right now, those two steps are very much driven from a cost perspective.
Oh, well, this one says cheap, so that one. So this first pass, it helps, like, we don't use the heavy reasoning model on the whole thing.
Exactly.
So the first pass and then
in the first catch results. Yep.
The last question about how it works is it good? Does it do a good job?
Yeah. So this is where, we do kind of a variety of mechanisms here. Obviously, as any kind of AI native or AI driven product, we have evals that we build, that we maintain, that we're adding and kind of constantly iterating on to make sure we understand the performance of our own models and prompting and all of that day to day. But then kind of there's an industry best practice standard here called the OWASP benchmark. OWASP stands for Open Web Application Security Project. And so within OWASP, there is a benchmark where it is basically like the industry standard evaluation framework for SAST tools. And so high level, right? Literally think of it as like a large set of tests. So you have thousands and thousands of different examples, both examples of secure code and insecure code and different types of vulnerabilities. And it's a known set of, okay, these are vulnerabilities that are present and these are ones that are not present. And the expectation is you run your different SAST tools against them and you're basically evaluating the output. To what percentage accuracy did you find the relevant vulnerabilities? What is your false positive detection rates, true positive detection rates, recall precision, etc. And so in our case, what we do, and we run these benchmarks constantly, both on our existing SAST tool as well as our AI native SAST tool, and we look at competitors, benchmarks, all of that. And what we found is that for our own existing Datadog static analyzer compared to our AI native static analyzer, we saw a 50% increase in accuracy by moving to the AI native SAST. So, and this was kind of across the entire kind of spectrum of categories that a WASP benchmark covers. But obviously it's a huge jump, right? We're talking like 90% accuracy at that point in the AI native approach, which is, it's all about, like we said at the beginning, right? How do you reduce the false positive rates? How do you give developers better context? How do you make things more actionable? And it all starts with how good are the detections themselves?
What if I'm a Datadog user and I want Datadog to manage this? Is there a product I can get?
Yes, there is a product. It's actually the code security product under that's part of our security offering here at Datadog. You can go to the product page for more information, but it's as simple as, you click a few buttons, you integrate your source control, you select which repositories you actually want us to scan, and then everything kind of just flows automatically from there. And then bing, bing, boom, you have results, you have detections. Hopefully, you actually have zero detections, but
you have peace of mind is what you have, right? Awesome. Well, thank you so much, Bahar, for sharing your time and your expertise today. I really appreciate you.
Yes, thanks for having me.
And thanks everyone for watching. Bye.